Hello, everyone. My name is Jonese Pipkin, and I had the pleasure to work underneath the guidance of Dr. Yvette Kuiper and Allison Severson at the Colorado School of Mines. Now, we were focusing on the structural analysis of bedrock geology quadrangle maps in the southeastern New England Appalachians. So for a little introduction, we were looking specifically at the Neshoba-Putnam region, which is depicted right here, as well as the Western Avalon, which is along the eastern border of the Neshoba-Putnam, and the Merrimack Belt, which is along the western border of the Neshoba-Putnam. It was already understood that there was high-grade metamorphism in the Neshoba terrain as well as the southern Avalon terrain, but in the surrounding terrains it was low-grade. So we weren't sure why that was so, and we wanted to analyze and interpret the rock structures in the terrains within and around the terrains. For background information, the Neshoba-Putnam was actually formed through arc-back-arc volcanic activity and sedimentation. Now, in the image to the right, you can see that through the subduction of the oceanic crust, volcanism was started, and behind the volcano, you can see the sedimentation that built up, which was the processes that made the Neshoba-Putnam. Now, an orogeny is a mountain building event, and so the Acadian orogeny is an important orogeny that affected the Neshoba-Putnam, and that was when the Avalon terrain accreted to the eastern border of the Neshoba-Putnam, which lied within the Gandaria microcontinent. And during that time, it was also significantly metamorphosed, creating the deformation for the most part. All right, to begin to interpret and analyze the structures within the Neshoba-Putnam, I first digitized the points that I would be analyzing and compiling data on. Now, I did this by looking through the 36 quadrangle maps, which you can kind of see in the map to the right, the different segments of the quadrangles, and it amounted to over 18,000 points that I cycled through twice to get data and compile information on. This map specifically depicts the dip measurements that I will later expand on. And so here we are. I compiled information on the dip measurements and strike measurements. Fortunately, the dip measurements were provided in the quadrangle maps. However, the strike measurements I had to measure myself using an ArcMap tool called the rotation tool. Now, dip happens to be the angle below the horizon of the declining plane, and the strike is the compass direction of the horizontal line of the declining plane. So in this image here, you can see that the dip angle would be below the horizon, right there, and the strike would be the line along the horizon in the opposite direction, the compass direction. And so the map here depicts the strike and dip information that I compiled. The difference between this map and the former map is the symbology. The previous map was just the points of the locations that I was looking at, whereas in this map, it actually includes the bedding symbol, which you will see later, which helps actually visually represent the dip variations in the Neshoba terrain and the surrounding terrain. And so the red color happens to be steeper dips, and the pinkish to white color is the more shallower dips. Next, I looked at the structural classifications of the different points of bedding and schistosity and isosity. And so throughout the quadrangle maps, I was looking for the bedding symbol and the schistosity symbol. So this line right here is actually supposed to be vertical. Sorry. And yeah, so I was looking for these symbols throughout the map. And for schistosity, that is the mineral arrangement of, or the arrangement of minerals in a metamorphic or deformed rock. And so in the image to the right, you can see that schists and rocks have layering, but they differ from gneiss because the gneiss in rocks actually has the bending look to it as well. And so the map above is my resulting map that I created, and it includes the different structural points that I plotted and compiled information on in the terrains as well as around the terrains, and these areas that we consider domains. And domains happen to be different rock types that differ from the surrounding terrains that they may lie within, or either areas where they had strike or dip trends that we wanted to look at further. So getting into some of the results. First, these are stereographic projections that I mentioned in the last slide. Now, these are actually depicting the points of bedding and schistosity and gneiss as poles. And so poles are going to be the 90-degree offset of the strike to the plane. So the red line in each of the stereographs happens to be the theoretical plot or plane of the dipping structures. And so for the Neshoba terrain in the top right, you can see that the pole cluster is plunging towards the southeast, and so therefore the plane would be dipping towards the northwest. And based on the proximity of the clusters to the circumference of the stereograph, that determines the steepness or the shallowness of the plains. And so the Neshoba, I'm going to say it again, the clusters are plunging towards the southeast, and so therefore the plane is actually dipping steeply to the northwest. Now for the Putnam terrain, which is in the bottom left, the cluster is plunging towards the eastern, or well, kind of sort of the southeastern degree, and so the plane would be plunging, or excuse me, dipping towards the northwest to west, and for the rest of them. Now, for the domains that we focused on, we looked at the central Avalon terrain, which is depicted here, the southern Avalon terrain in the bottom, which comes beneath the Putnam terrain, the Fishbrook gneiss, which is located up here, the Andover granite, which is to the left of it, and the Rubens Hill complex, which actually lies between the Neshoba terrain and the Merrimack terrain, or belt, excuse me. The Rocky Pond slice also lies in the same region. Now, so the stereographic projections for these, as you can see, are depicting the same thing, the clusters, which are the 90-degree, or the normal to the plane. And for the Fishbrook gneiss, the plane would actually be dipping to the northeast. The Andover granite would be dipping to the northwest. And the Andover granite and the Rubens Hill complex actually have a similar dipping plane, and so that would be to the northwest as well. The Rocky Pond slice domain is dipping to the northwest too, and the Central Avalon would be dipping towards the northeast. And then finally, for the Southern Avalon terrain, it would be dipping towards the northeast as well. And so what was interesting from this data here is that the Rubens Hill complex, or excuse me, the Rocky Pond slice and the Fishbrook gneiss happen to lie within the Neshoba terrain. However, the strike and dip orientations differed, which is interesting for us to note since it's lying within the terrain, so you assume that it has a similar dip. However, this was different because that they happen to be rock blocks. But going back to the Neshoba terrain, the strikes, and these are supposed to be vertical too. My apologies. The Neshoba terrain actually differs as you travel down from the northern part to the south. And so the strike here is striking towards the northwest. However, in the bottom, it strikes more to the, oh, I'm sorry, I looked at the wrong one. The strike here for the upper Neshoba terrain is striking towards the southwest, but as you transition down to the south, it's going, or striking towards the south-southwest. And then the Fishbrook gneiss, and that is possibly because we suspect it's going to be because of indentation or the folding event that could have occurred during the accretion of the Avalon terrain, which is roughly right here. Now for the Fishbrook gneiss and the Rubens Hill complex, like I said before, for the Rubens Hill complex, we suspect that it might be a rock block, which is just an area of rock that differs from the surrounding rock terrain. And so the strike here is going to be towards the northwest, and then for the Rubens Hill complex is towards the west-southwest. And again, the differentiation is probably because of it being a rock block. Now for the rest of the terrains that we are looking for, the Putnam terrain is right here, and as you can see in the southern half, the strikes and the dips actually alternate between shallow and steep. Not only are the dips alternating, but they also, the strike transitions from being more striking south to more striking south-southwest. Then for the Central Avalon terrain, which is roughly right here, it strikes, it's a westerly strike. However, it does differ, and it kind of follows like a fold hinge right here, but we didn't get to the point to actually analyze that part of the data yet. That's just what we suspect at the moment. And then for the southern Avalon terrain down here, the strike and dip vary, and not only do they vary, but they follow points of curvature. And so you can kind of see the swirly appearance in the lower half here, and that we suspect is due to metamorphic, high-grade metamorphism, as well as partial melt in the area. And so for the other two regions, the central Avalon and Putnam terrain, again, we think that the strike and dip vary based off of the accretion of the Avalon and through all the deformation that occurred during that time. So for you guys' understanding, this was mostly just the first step of analyzing what happened to the Neshoba-Putnam terrain. And so for future research, we suggest that we look at the lineations of the different points in the area and compare that to the lineations as well as the fold hinge lines and their orientations, and compare that to the magnetic and gravitational anomalies so that we can have a better understanding of what caused the deformation in the terrains. And I would like to thank everyone that assisted me in this project, including the UNAVCO staff and the NSF for granting or funding the RESESS program. Thank you.
Great, Denise. Do you have any questions?
So I'm curious, could you clarify for me how you would determine if something is striking south versus if it's striking north?
Sure. So let's see. The strike, okay. So do you understand striking? You understand striking dip, right? No. Okay. So back to this image, you can see here that the plane is declining. So this is imagine this being as like the rock that you're studying. And as it dips below the horizon, this is going to be the angle that you're looking at. And the strike direction would be like compass direction, or if you're using right-hand rule, you would place your hand like along the bedding, and so that would be your dip. So these fingers would be your dip, and your strike would be towards the compass direction that it's striking, if that makes sense. Okay. And so I guess we could do this one. You can kind of see the lines of the bedding symbols, how they're like going diagonally to the to the southwest. And so that would be considered a strike because the diptych, which is like the dip direction, is actually going in this direction. So the strike, if you put your plane or your hand along that, your strike would be to the southwest.
Okay, thank you.
Okay.
Thank you, Janice. Could you go to your one of your wrap-up slides that showed the orientations of everything? The one that had the swirly patterns?
Sure.
Yeah, so the swirly patterns there, it looks like those are measurements on foliation, whereas everything else is on bedding. So could the difference in the patterns there be because you're measuring foliation in one hand and bedding in the other?
Well, for my stereographic projections, they actually combine, we actually looked at them together. So it was bedding and schistosity, nisosity, or foliation. So the last part of your question, I'm sorry.
Well, I guess you answered it.
Okay.
Here you've got the foliation symbol down below, and then you've got the bedding strike and dip above. But it sounds like the data that this is based on are just combination of both of those.
Yes.
Great, thanks.
Other questions? Brittany. Oh no.
How long does it take to plot one point?
It doesn't take a long time to plot the points, but for the quadrangles, it can take like a day if there's like 500 points in there.
To make the whole map?
Oh, to make them, which map?
To plot one point, how long will it take you? Like just in general?
Well, okay. Well, I broke it in half, and so I did the locations first, and then I went back and compiled the data. That's why I had to go through all the points twice. And so it just depends on how fast you go through it. I watched a lot of movies, and to keep me focused, it really does help because there's a lot of data that we were compiling. But so it took all 9 weeks for everything.
Yeah. Well done. Thank you, Janice.
Thank you.